Okay, let's get started. Sorry for having no intro problem today. We'll be going through a bunch of definitions that will be foundational for this class and next class on linear algebra, so there wasn't a problem that made sense outside of those definitions, but I'll come right back to it as soon as possible. Let's start out with some course announcements. First, Vincent's optional list of practice problems is available now on Slack for anybody who's interested in that. Second, Monday's class attendance is optional for anyone who will be observing Yom Kippur. No need to email me or let me know. It's just optional attendance. Are there any questions about class in any way? Okay. So we will be starting linear algebra today, and there will be a couple of classes on this because linear algebra is a huge topic and it will be really useful in a lot of different ways. So today we're just going to start out with some basic definitions of vectors and matrices and really try to dive into the math behind why those things make sense. And we'll continue that on Monday. So let's start out with vectors. What is a vector? So we're going to be looking at real vectors, so vectors over real numbers. A real vector is a tuple of real numbers. If the vector is v, then we often denote them with subscripts v1 through vn. We can write that v is in Rn, so the real numbers raised to the nth power, and say that v has dimension n. One can also work with vectors where the entries v sub k are complex numbers or rational numbers or really anything that is what's mathematically called a field. We won't go into that. We probably won't need anything besides real numbers. Order matters in a vector, so 2, 1, 1 is not the same as 1, 2, 1, for example. When working with real vectors, we would say that real numbers are scalars to distinguish them from vectors. So for example, 2, 2 would be a vector and just 2 would be a scalar. Sometimes there's a distinction between 2 in brackets, meaning that it is a vector in r to the 1 versus the scalar, just 2, but I'm going to gloss over the distinction between that. And in some programming languages, you'll also run into that. So some basic properties. Vector addition and subtraction are defined just performing those operations component-wise, sort of in the way that you would imagine. If you're adding two vectors, you just add the first component, add the second component, and so on all the way to the last component. Likewise, if you're subtracting two vectors. If you're doing multiplication or division by a scalar, so by a real number, that also is going to work component-wise. If you multiply by some c, you can just multiply each of the individual entries by c. Likewise, if you're dividing by c, you can just divide each of the individual entries by c. Okay. So for example, if v is equal to 1, 0 and w is equal to 0, 1, what is 5v minus 2w? Awesome, 5, negative 2. Yep. Okay, so we often will think about vectors graphically. There will often be vectors portrayed by points in Cartesian coordinates. So if you have a vector in 2 dimensions, for example, you can visualize it like this. And there are two sort of subtly different things going on here there is representing a vector as a point, and there's representing a vector as sort of an arrow. These are just sort of different ways of thinking about the same underlying mathematical object. If you're thinking of vectors as points, you can think of them just as, the point x, y. If you're thinking of them as arrows, then the arrows should have a fixed length and a fixed direction. This is very convenient if you're trying to think about addition or subtraction of vectors. So here, the vector v is this arrow. The vector w is this arrow. Now you can represent their sum as following this arrow and then following this arrow. And that will give you this long arrow. Now that can be pretty easily proven if you're going back to these Cartesian coordinates by saying that, okay, well, this point has this amount of y, and this point has this amount of y. And if you add this amount of y plus this amount of y, you're going to get the big point over here. Likewise, if you're adding this amount of x and this amount of x, you're going to get this full amount of x over here. And that can be made rigorous very easily by just drawing some boxes on this parallelogram. Likewise, if you're trying to work out what the difference of two vectors is, you can think of here it's difficult to remember which one is going, where the head of the vector is and where the tail of the vector is. So if you're looking at v minus w, then the way that I remember it is w plus v minus w is equal to v. That means that the vector v minus w should come from w to v. It's just the same thing as v plus w being the sum of v and w. V is now the sum of w and v minus w. Any questions? This also allows one to think about scaling vectors in scaling a vector by a scalar, multiplying it by a scalar. That's just changing the length of the vector. Okay, so we'll use all three of these. We'll use the coordinate representation of the vectors. We'll use the arrow representation of the vectors, and we'll use the just no geometric representation at all. So what are norms of a vector? So a general way to write a lot of different norms of a vector, I'm not going to go into the mathematical definition of what a norm is, but a norm is a way to take a vector and come up with a scalar from it. There are various different kinds of norms, and norms actually have to satisfy some technical properties, in particular the triangle inequality. But we don't have to go into that. So the norms that you'll probably be running into are the LP norms, or just sometimes they're called P norms. So if you're wanting to define these, P norm for any p greater than or equal to 1 of a vector is just the sum of the pth powers of the individual entries of that vector raised to the 1 over p. So what is the L1 norm of x? Sorry, I sort of said the pth powers of the absolute values of the entries. What is the L1 norm of x? Yep. So this is sometimes called the taxicab distance or the Manhattan distance. It is the sum of the absolute values of the entries of the vector. And that's just because if you had a grid in high dimensions, you're just going along the axes. You're going along x, then you're going along y, then you're going along z, and you're seeing how long it takes you to get to the vector by going along all those different components. Okay. So this is the L1 norm because p is equal to 1, so all of these are 1, and this is also 1. Okay. The most common norm is the L2 norm, and this is given by the square root of the sum of the squares. Okay. Often this will just be written as the norm of x because often the 2 is assumed, but it's generally good practice to write the 2 in. So let's look at a geometric interpretation. Geometrically, the L2 norm of a vector is equal to its length. So in 2 dimensions, this is what it looks like. If you have a vector u, components u1 and u2, then by the Pythagorean theorem, the length squared is just equal to the sum of the squares of the individual of the legs of the triangle. But those are just the entries of the vector. So if the vector is u1, u2, then the square of its L2 norm is going to be the square of its length. So the L2 norm is equal to the length. There's a question. In the notation LP norm, why are we using both symbols? So LP has to do with sort of the mathematical framework surrounding this particular norm. The L is a relic of that mathematical framework. That's one of the reasons why many people just say the P norm, it's shorter, and if you're not thinking about LP space, there's no reason for you to use the L. So often people would say the 2 norm instead of the L2 norm. Why is this true in higher dimensions? Why is the length of the vector equal to its L2 norm, Euclidean length? This is a 3-dimensional picture. How can we prove this in general? Even just for this 3-dimensional picture. So in this 3-dimensional picture, as people are suggesting, we can use the Pythagorean theorem a couple of different times. So here we can use the Pythagorean theorem once down here. x1 and x2 and h form a right triangle. x1 squared plus x2 squared equals h squared. And then h squared plus x3 squared is equal to the length of this full vector squared. So if we combine those two, we get x1 squared plus x2 squared plus x3 squared equals the length. But again, x1 squared plus x2 squared plus x3 squared is equal to the L2 norm of x squared. Okay. So this is why all of these things are connected, why in 3 dimensions, and it's pretty easy to see that in higher dimensions, though it's hard to visualize, the L2 norm of a vector is equal to the length of that vector. Okay. Now, you will often see the L infinity norm as well. What is the L infinity norm? The L infinity norm you can get a sense of by taking the norms, the P norms, as P gets larger. So for example, the P norm of this vector, 1, negative 10, 8, 0, if P equals 1 is equal to 19, 1 plus 10 plus 8. The L2 norm is some nasty number, but around 13. L5 norm is 10.58, going to the L20 norm, 10.01. So what is happening here as P gets larger? And why? We're not going to do a formal proof because we haven't gone to the calculus of limits, but it is indeed converging to the value 10, which is importantly the maximum absolute value of the entries. Now, why is that the case? Well, as p is large, and we will prove this later on, but as p gets large, the sum of the pth powers of all of these things is dominated very quickly by the largest absolute value to the pth power. So you can basically forget about all of the others as p goes to infinity, and this just becomes the pth root of the pth power of the max element in absolute value. So this is something that you will see in many applications, the L infinity norm being a way to measure vectors. And it is technically a mathematical norm. Now, there is also something that you will possibly see called the L0 norm. For what this means is that you are looking at the number of non-zero entries in the vector. This is also called the sparsity of the vector. And an intuition for why this is called the L0 norm is if you set p equal to 0, this doesn't really make sense if you set p equal to 0, but the 0th power of something is equal to 1. But 0 to the 0 could be equal to 0. So basically, all of these are 1 unless the entry is 0, in which case it's 0. So that's the sort of intuition for why the L0 norm is that. However, there are problems with this, most particularly because it's not actually a norm. There's one property of a norm, which is if you multiply x by a constant, a scalar, then that should change the norm by the absolute value of that scalar, but it doesn't in this case. In particular, it doesn't change the norm at all. If you multiply say 1, 0 by 2, you get 2, 0, but that has the same L0 norm. So it's not really correct to call it the L0 norm. A lot of people do. Generally good to use other language if you're trying to be mathematically correct. And yes, there's a question about the to the 1 over 0. There are problems with this in general. I'm not going to go into the limiting behavior of this. There is limiting behavior as well, but that's not necessary for us now. I was just trying to give an intuition for why that's the case. Okay. Questions? Let's move on to dot products. So the dot product, or the scalar product, that's another way of another name for it, of vectors x and y is given by the sum of the component-wise products of the vectors. And this is extremely important. And even if you've seen it, there's a lot of deep math that's going on under the hood. So as an example, if x is 3, -1, 0, and y is 2, 1, 2, then the dot product is the sum of 3 times 2, -1 times 1, and 0 times 2. So that would be 5 in this case. Now, what is x dot x? Yeah, it's the L2 norm squared. It's just if you plug that into the definition, it's the sum of the squares of the individual components of x, which is just the L2 norm squared. Awesome. So this is a fundamental property of dot products, which is really one major reason why they are so useful. Prove that the dot product between vectors a and b is equal to the L2 norm of a times the L2 norm of b times the cosine of the angle between them. The reason why this becomes extremely useful is, there's a way in which dot product is the similarity between two vectors. So you will see this in, for example, machine learning's cosine similarity, where if two vectors are aligned with each other, then the angle between them is very small and the cosine is very large. Dot product is very large. This is an intuition. So how would we go about proving something like this? Let's draw a picture. If something is fundamentally geometric, then we should definitely be looking at it geometrically. And I'm not putting axes on here because these vectors could live in any number of dimensions. They could be in n-dimensional space, but in n-dimensional space, there is an angle between them. So we're looking at basically the two-dimensional plane in which these two vectors live. So there is a triangle of one vector, the other vector, and the difference between them. Now, these things form a triangle, so we know the lengths of the sides here. A, B, and A minus B. The lengths of the sides are just the L2 norms of those things. What can we use? Okay, we can use the law of cosines. So if you haven't seen this before, and we will prove it afterwards, there's a geometrical result called the law of cosines. It generalizes the Pythagorean theorem between the sides of any triangle. So in the Pythagorean theorem, it says that a squared plus b squared equals c squared. But that's only true for right triangles. In general, you can say a squared plus b squared equals c squared minus 2 times the length of a times the length of b times the cosine of the angle between them. And we'll prove that in a moment. But for the moment, let's just assume that this is true. Notice in the Pythagorean theorem that the angle is 90 degrees. And so the cosine of the angle is equal to 0. So that means that a squared plus b squared equals c squared. Now, we can substitute in our lengths, L2 norms of a, b, and a minus b, and we get this. That's just the same thing rewritten for our particular case. Oh, let's just expand that. The L2 norm of a is just the sum of the squares of the entries of a. The L2 norm of b is the sum of the entries, squares of the entries of b. And likewise for the difference a minus b. If we expand this, we get this. And rearranging a little bit, and you can get these squares and we get these products. If we cancel out all of the squares, then and move these products over to the other side, we get the 2a1b1 plus 2a2b2 plus so on, all the way up to 2anbn is equal to this other term, 2 times the length of a times the length of b times the cosine of theta. And if we just divide by 2, that's just the dot product of a and b equaling the L2 norm of a times the L2 norm of b times cosine theta. Are there questions about this? The nice thing about the law of cosines here is that it allows us to take a problem that's based in coordinates, which are sort of ugly, and turn it into pure geometry, turn it into a single triangle. And so this holds for any number of dimensions, even if your vectors are extremely high dimensional. Okay, now just for the sake of completeness, let's prove the law of cosines quickly. Here's a triangle, ABC. Here are the lengths A, B, and C. Let's just prove the law of cosines quickly. We can break up the triangle into 2 smaller triangles. We can write a squared is equal to x squared plus h squared, where h is the altitude, the perpendicular line from B to AC. So a squared equals x squared plus h squared, and what is h squared? Well, if we apply the Pythagorean theorem to this other right triangle, c squared is equals a squared, h squared plus b minus x squared. So h squared is equal to c squared minus, h squared equals c squared minus b minus x squared. If we expand this out, then we get this. The x squareds beautifully cancel. And rearranging, we get that a squared is equal to c squared minus b squared plus 2bx. Now x is in this right triangle here. And we know that by the definition of cosine, cosine in a right triangle is x over a. It's the angle here. Cosine of c is equal to x over a, so we can just rewrite this as 2ab cosine c. And moving the b squared to the other side, this is just the law of cosine. Are there questions? Where do the sine and cosine functions come from? So I'm not going into the definitions of sine and cosine, but you can just define them as the adjacent side of a right triangle over the hypotenuse and the opposite side of a right triangle over the hypotenuse. There is another definition that we will see with Taylor series, but for our purposes now, all we need to know is that sine of angle C is x over a, and cosine of angle C is x over a, and sine of angle C is h over a. But the sine and cosine functions are very fundamental in math, and they have many different definitions and motivations. This proof doesn't work for obtuse triangles. If the angle C is greater than 90 degrees, you'll have to break it up slightly differently, but it will be just the same kind of proof. Okay. So what is the dot product of two perpendicular vectors? Yep. Dot product is just 0. We've seen that the dot product is equal to the norm of one times the norm of the other times the cosine of the angle. If A and B are perpendicular, then the angle is 90 degrees, so the cosine is equal to 0, and therefore A dot B is equal to 0. This is extremely important. Okay, now we've taken a look at matrices for a while. Vectors, sorry. Let's look at matrices. A matrix is a set of real numbers, which you can index by indices between 1 and m and indices between 1 and n. This is often represented as a set of rows and columns. These are the rows of the matrix, and these are the columns of the matrix. So this is a matrix with m different rows and n different columns. This is often written that A is in R to the m cross n. That's the way to sort of say the space of real matrices, of dimensions m and n. If m is equal to n, we say that A is a square matrix. In particular, matrices can be thought of as a generalization of vectors to some extent. If m is equal to 1, then we have, oh, I'm sorry, there is a typo here. That should be, these two should be swapped. If m is equal to 1, then A is a row vector, such as this one, the second one. And if n is equal to 1, then A is a column vector, 1, 0. It's just if there's only one of these columns or only one of these rows. And you can think of these just like vectors, 1, 0. Though we'll see what it means to be different, what's slightly different between a row and a column vector. So some basic properties of matrices. Matrix addition and subtraction are defined just as with vector addition and subtraction, performing these operations component-wise. So if you want to add together two matrices, you just add together each of the individual components. And likewise, if you want to subtract those two components, you subtract, if you want to subtract the matrices, you subtract the components. Likewise, multiplication by a scalar also works component-wise. If you're multiplying by any real number, you can multiply all the entries of the matrix. Okay, so those are the basic properties, but now let's get into the real meat of the thing. Why are we interested in matrices? Well, a fair amount of it is because of matrix multiplication. Let's start out with matrix vector multiplication. But before we do that, there's a question. Writing the space of, I'm happy to talk about that other notation. I think that from a mathematical perspective, it's very common to write A is in R to the M cross N, but there are other notations. Yeah. Okay, so let's define matrix vector multiplication. If you have a matrix that is M by N and a vector that is N dimensional, then the product is going to be defined like this. You can take the dot product of the vector and the first row of the matrix, the dot product of the vector and the second row of the matrix, and all of these dot products you're going to stack into another vector. We often write the product of a matrix and a vector as the product of the matrix and the column vector. So it'll be clear why that's the case, why we're writing this vector vertically, but often just for the sake of notational convenience, we will write a matrix and a column vector if the vector is being multiplied on the right of the matrix. So again, the product of a matrix and a vector is just the vector formed by the dot products of that vector and the rows of the matrix. Now, in particular, notice that the dimensions have to match up. You have to have the number of columns in the matrix be the same as the dimension of the vector. And also, you get the number of rows in your final vector, or the number of entries in your final vector is the same as the other dimension of the matrix, which is M. So in some sense, these two n's cancel and you get one dimension of M. Here is an example of matrix multiplication. If you take this matrix and multiply it by this vector, 1, 1, 0, dot 1, 0, 0, is that 1 times 1 plus 1 times 0 plus 0 times 0 is equal to 1. If you dot this with this second row, you get 2 because these entries cancel out, the first and third entries cancel out. And likewise with the third row. So that's an example of a matrix vector product. Intuitively, you can think of matrix vector products as transformations of vectors. So we will see a couple of different versions of this. In particular, next time we can take a look at orthogonal matrices and rotation matrices. But for a moment, let's take a look at simpler transformations. First, the identity matrix, which is the transformation that does nothing at all. The identity matrix is the matrix of entries where the diagonal entries are equal to 1 and all of the other entries are equal to 0. For example, the 4x4 identity matrix is equal to this. And the key point of identity matrices is that if you multiply by a vector by an identity matrix, then you get the vector back. Now, this is sort of true in a way that you can see by example. Here, if you dot this, if you multiply this vector by this matrix, you can see the dot product of the first row with this vector is going to be just picking out the first entry of the vector. The second row is going to pick out the second entry of the vector. The third row is going to pick out the third entry, and the fourth row is going to pick out the fourth entry. So each of these dot products is going to take exactly one entry of the vector, and that will give you this ultimate vector at the end. There's a question. Taking derivatives of matrices and vectors, we will absolutely cover derivatives with matrices and vectors. It is definitely something that is thorny and a good thing to talk about. We will talk about it, just not yet. Okay, so let's look at a special kind of matrix, permutation matrix. If a matrix has all entries 0, 1, with exactly 1, 1 in each row and exactly 1, 1 in each column, then it is a permutation matrix. Why is this called a permutation matrix? Well, if you have one of these things, and you can see that this is an example of such a matrix, so this is 1, 1 in each row and 1, 1 in each column. Go through and check all the rows and all the columns. Then if you multiply a vector by it, then you get a permutation of the entries of the vector. Now, why is that? Well, if you think about it, let's take a look at the first row. The first row is going to pick out the 3 from this vector if you do the multiplication. The second row is going to pick out the 1. The third row is going to pick out the 2, and so on. Because there's exactly 1, 1 in each row, we're going to pick out exactly one entry with every one of these dot products. And because there's exactly 1, 1 in each column, we're never going to pick the same entry more than once. We're going to pick one entry, but it's going to be different for each of the rows. So that means that we end up with a permutation of the entries. Question, is the identity technically a permutation matrix? Yes, it is, very much. Any questions about permutation matrices? One could get into an entire field of studying permutation matrices, which, so what is the use of permutation matrices? There are so many different mathematical uses. This is basically a way to think about permutations of entries in a vector. And this turns up in many, many different contexts. In particular, permutations matrices show up in a branch of math called representation theory. But it will also become extremely relevant when we talk about the determinant and thinking about the sign of a permutation. The sign of a permutation is basically a way to assign plus or minus 1 to a permutation matrix. And spoiler, that is just what the determinant of a permutation matrix is. If you haven't seen determinants, then no problem there. But it will be important in understanding how, for example, swapping 2 rows or columns of a matrix changes the sign of the determinant. And permutation matrices are fundamentally important in group theory in general. So a group is a mathematical object where you define multiplication of elements within the group, and you define inverses of elements within the group. And permutation matrices are essentially one of the fundamental groups and really important for understanding all of group theory. I hope that that helps a bit. You don't have to think of permutation matrices necessarily as matrices. You can think of them sort of more abstractly as elements within the group of transformations that is permutations. Okay, so matrix multiplication. Here is the thorny definition, but it's very simple. If we're trying to multiply 2 matrices, it's just like multiplying a matrix by a vector. We just multiply every single column vector of B by the matrix A, and then we take, remember that the matrix A multiplied by a column vector is going to be a column vector. So we take the resulting column vectors and we just concatenate them. So this first column vector is just this first column of B multiplied by the entire matrix A. So the first column is this column multiplied, dotted by this row, dotted by this row, dotted by this row, and so on. That's what this column is. The next column of the result is this second column of B multiplied by the entire matrix A. So this column dotted with this, dotted with this, and dotted with this. And then the final column is this final column of B dotted with every row of A again. Okay. So matrix-matrix multiplication is basically just like matrix vector multiplication, and matrix vector multiplication is basically just like the dot product. So everything is built on the dot product. Importantly, what is the dimension of the resulting matrix? Well, in order for this to work, the inner dimensions have to match up. If you're multiplying A and B, the second dimension of A has to be equal to the first dimension of B. So here we have B being an n by P matrix and A being an m by n matrix. And then you get a result where the matching dimensions cancel and you get a matrix which is an m by P. And you can just check that that's what, in fact, we got. Number of rows is equal to the number of rows of M, and the number of columns is equal to the number of columns of, the number of rows of A and the number of columns of B. Okay. And then here is why matrix multiplication is a reasonable thing to do, because we've just created this really long-winded definition. The important thing is that this is associative. That is, you can group the terms A and B. You can also group the terms B and C. And this will give you the same result. Now, this is not to be taken for granted. In real numbers, this is very much true. 2 times 3 times 4. Doesn't matter if you multiply the 2 and the 3 first or the 3 and the 4 first. But it's not immediately obvious that this is true for matrix multiplication. So let's see why this is true. We're just going to look at the proof for A being a vector and C also being a vector. A is a row vector and C is a column vector. But the same argument will hold. We're just stacking up rows and stacking up columns in order to get the answer. What are the dimensions if we did the product A, B, C with these dimensions of matrices? What are the dimensions of the product? Yeah, it's 1 by 1, or you can think of it as a scalar. Okay, so multiplying, let's do A times B. A times B is just going to be a row vector because we're multiplying a 1 by m matrix with an m by n, and we're going to get a 1 by n vector out, a row vector. So what we get is the dot product of this first column with this row, the dot product of the second column with this row, and so on. Now, what if we multiply that by C? Well, C is a column vector, so we're just dotting this with a column vector, C1 through Cn. And so the final output is going to be equal to this. You can think of it as AI times Bij times Cj summed over all possible I and j. Okay. Now, that's A times B, then multiplied by C. Let's do B times C and then multiply by A. B times C is just going to be a column vector multiplied by all of the rows of B. And so we're going to get these dot products arranged in a column vector. And so if we multiply that by A, which is a row vector, we're just having the dot product of 2 vectors, A and BC. And if we go into the details of that, we're just going to get the same thing out, which is, again, the sum of AI, Bij, Cj, as I and j vary. So we see that A times BC is equal to AB times C. Cool. Are there questions? The amount of computation can greatly differ depending on the chosen multiplication order. Yes, it will be extremely useful that we can change the multiplication order. Is it obvious if we think of matrices as transformations? Because we're essentially doing some transformations in some order. C, then B, then A. It's not necessarily obvious, I think, because it's not clear that transformations always work like that. You could imagine some transformation that isn't a rotation, for example, where the order does matter. And associativity is not a rule that always holds from mathematical operations. So for example, if you were doing this with exponentiation, a to the b to the c, well, sorry. Yes, a to the b to the c is different than a to the b to the c. So this is an example of some situation where you really want to be careful with the order of operations. Because it's, the reason why it feels so obvious is basically just because we said it is multiplication. If we wrote it like exponentiation, then it would seem less obvious. It's just because we're really, really used to not having to write parentheses when we do multiplication. So whenever you see a new mathematical operation, you should be aware that these properties are not to be taken for granted, basically. Okay. So you are right that transformations like permutations do have this property. If A and B are permutation matrices, then B acts as a permutation of X. So if we apply A after B, then A of B of A multiplied by BX is also a permutation of X. Because we permuted X once and then we permuted it again. That's clearly another permutation. So since we can just regroup, A times BX is equal to AB times X, so the matrix AB is also a permutation matrix. Done. You immediately now know that if you multiply two permutation matrices, you get another permutation matrix. Commutativity. Is AB equal to BA? No, they do not necessarily commute. Okay, so why is that the case? Well, here's an example of two matrices, multiplying two matrices in one order and getting one result, and multiplying them in another order and getting a completely different result. And in general, we should remember that if you multiply an m by n matrix and an n by p matrix, then AB is defined because these inner dimensions match, but BA isn't defined if m is not equal to p. So not only can these products not be the same, one of them could not even exist. And in general, even if they do exist, if you had A being an m by n matrix and B being an n by n matrix, then the products are both defined, but the first one is an m by n matrix and the second is an n by n matrix. Okay. So finally, let's look at the transposing matrix. If A is some matrix, then the transpose, AT, is the matrix where you have just reversed the rows and columns. Easier with a picture, just flip the rows and columns. This matrix flipped is this. The diagonal matrix is going to stay the same. The diagonal of the matrix is going to stay the same, but you've flipped all the other entries around the diagonal. Here is an important fact, which I will not go into, but you can think about as, if you go back to the definition of multiplication, if you multiply two matrices and then take their transpose, it's the same as taking the product of the transposes, but in the other order. Now, how can you remember that? Well, if you tried to take the transposes without changing the order, then again, these matrices might not have matching dimensions. M by n, n by p. If you transpose both of them, you have n by m and p by n, and that wouldn't work. But if you reorder them, then you have p by n and n by m, and they can multiply. That's one intuition for why this might be true, but you can go and just check that since rows and columns, if you change them to columns and rows and do it the other way around, it will all work. Oh, and a simple property of transposes, matrix transposes, is that if you take the transpose twice, then you end up with the matrix itself. Here is an example of how the products and transposes work. If you take this matrix times this vector, you get a column vector out. If you take the row vector and you multiply it by the transpose of the matrix, then you get the corresponding row vector. Okay. And now finally, since we talked about the identity matrix before and how it's useful in multiplying vectors, let's just see how it deals with matrix products. So if A is the identity matrix and X is a vector, then we know that AX is equal to X. And that means, since matrix products are just concatenations of matrix vector products, that AB is equal to B for any matrix B in R n times P. What's a quick way to see that multiplication on the other side by the identity is also the identity? Showed that if you right multiply the identity by something, then you get the same thing back. Why left multiplication? Why is that the case as well? Yeah, we can just use the transpose. So by the transpose formula we had, C times A transpose is equal to A transpose times C transpose. And that's equal to A C transpose because A is the identity matrix, and the identity matrix is the same as its transpose. And so that's equal to C transpose, so CA equals C. Okay. Next time we will be looking at linear algebra, 2, and continuing with determinants and eigenvalues, and actually seeing how this sort of foundation, I realize that many of you have seen some of these things before, actually becomes really important when we're using matrices for stuff.